Welcome to 9.6, absolute convergence and the ratio and root test. So here, we're going to talk about, in this video, absolute convergence. So given a series, summation of a sub n, we consider the corresponding series. Let's put absolute value bars around our function. That means every term is going to have absolute value bars around it, which then in turn makes every term positive as we add these together. So these terms are the absolute values of the terms of your original series. Our definition of a series of a sub n is called absolutely convergent if the series of the absolute values of all your terms is convergent in your series. So if our series of a sub n has only positive terms before we think about putting absolute value bars around it, then the absolute value of a sub n function is the same a sub n function. So absolute convergence is the same as convergence in this case. Again, when we say absolute convergence, that means we put absolute value bars around our function and its terms. Definition number 2, a series, the summation of a sub n, is called conditionally convergent if it is convergent but not absolutely convergent. That means we can show that it converges, but when we make the function absolute value bars around it and all the terms positive, it doesn't converge. So then that's convergent under the conditions where we don't get to put absolute value bars around it. All right, example. So given the series n equals 1 to infinity of negative 1 to the n minus 1 all over n squared, this is an alternating series, so is it convergent? We'll use our alternating series test. So again, number 1, we're going to take the limit of b sub n, so remove the negative 1 to the n minus 1, and you have 1 over n squared, and yes, the limit of that sequence function is 0. Next, we got to show that b sub n plus 1 is less than or equal to 1 over n, or less than b sub n, excuse me there, b sub n plus 1. This is where you put n plus 1 in for all the n's. All right, so we got rid of this. There's the b sub n plus 1. This is the b sub n. If I multiplied n squared up to the top of this fraction, take the quantity squared, multiply it to the top, you can see that, yes, this is a true statement. If you want to multiply this out, cancel the n squared, so you get 0 is less than or equal to 2n plus 1. That's always true. So again, both statements are true. So therefore, this series will be converging by the alternating series test. Now, is this series absolutely convergent? Okay, let's make all our terms positive. So we put absolute value bars around our sequence function. Doing that, well, negative 1 to the n minus 1 power is going to completely cancel out to become just a 1. Well, wait a minute, that's my p series. P is equal to 2, it's greater than 1, therefore it converges. So therefore, this original series is absolutely convergent. Okay? Again, absolutely convergent means we turned all the terms from alternating or wherever they got negatives, we turned them all positives, and it still converges. Example 2, given this series, wait, this looks familiar. We had this back in 9.5, example number 1. It was a harmonic series, and it was convergent. So 1 over n, the limit of 1 over n is 0. Again, we showed that it's decreasing. Multiply the n over n plus 1. You want to subtract the n, so 0 is less than or equal to 1 all the time, so that was true. So this was convergent by the alternating series test. Like I said, we proved that using the alternating series test back in section 9.5, example 1, if you want to check your notes. Okay, is it absolutely convergent? Put the absolute value bars around it. Now it becomes just 1 over n, but that's a harmonic series. And p equals 1, well, that's less than or equal to 1. The p series rule said that this then diverges. So since our original series is convergent by the alternating series test, but it's not absolutely convergent when we put the absolute value bars around our sequence function, the series is conditionally convergent. So theorem number 3, if a series is absolutely convergent, then it is convergent. Okay? Or if the series of the absolute value of a sub n converges, then the original series also converges. Saves time to check absolute convergence first. So we're going to look at a potential flow chart in how we want to do this. So we always look at the series when you get negative terms. Let's see if it's going to converge absolutely, because if it does, then we know it's also going to converge absolutely. If it doesn't converge absolutely, then we'll go do some kind of alternating series test. And if it does converge, then we know it's going to converge conditionally. So here's my absolute series. Does it converge? All right, so if we can say yes, then the original series converges absolutely, which implies, my series converges absolutely, which implies the original series converges as well. If this is a no, then we're going to try the alternating series test, which again is made up of step 1 and step 2. We got to show these two are true. If one is a no, then we saw back in 9.5, oh great, the limit doesn't equal 0. Therefore, it is going to diverge by the divergence test. So if number 1 is true, then we go to number 2. If number 2 is a yes, then our series is conditionally convergent. If it's a no, okay, there is no conclusion in terms of whether it converges or diverges. So we're going no to no. We have no conclusion of what's going to happen. Mouse got a little happy there. Let me go back. Okay, so this is our flow chart that we want to work with whenever they start talking about absolute convergence. Let's do this first, because if this is a yes, we're done. You can conclude that it's also going to converge as a regular series without the absolute value bars around it. So example 3, given the series n equals 1 to infinity of negative 1 to the n minus 1 power, we have n over n squared plus 4. Let's look at it absolutely. So again, put absolute value bars around it. That's going to remove the negative 1 to the n minus 1. So this will be a comparison test. So we're going to use our limit comparison test because, again, notice the plus sign in the denominator. Minus signs we can go with a direct comparison. Plus signs in the denominator, we have to go with limit. So number 1, let's make it look like something we can simplify it down to. So again, we don't need the plus 4. N over n squared simplifies to 1 over n. We just saw that's a harmonic series, so that's going to diverge. Now, to prove that that diverges, we still got to take the limit of the original a sub n over our new comparison function b sub n, and does it equal a constant c, which is finite. So my a sub n is the n over n squared plus 4 divided by 1 over n. But again, we don't divide these fractions when we take its limit. We're going to multiply by its reciprocal to get n squared over n squared plus 4. And again, using your horizontal asymptote rule if you wish, if the top leading power is the same as the bottom leading power, then the leading coefficient ratio 1 over 1 is your limit. So this is true. It is a positive. It's finite. It justifies that this series diverges. Okay, so the series is not absolutely convergent. It still might converge conditionally. So now we're going to go over here and treat and use our alternating series test. Wrong A word there. Alternating series test. So number 1, take the limit of just n over n squared plus 4. Yep, that's going to 0. The bottom's getting much bigger faster than the top. Or, again, you can use your horizontal asymptote rule. Top power on the leading term is 1. Bottom power is 2 on the leading term. That's automatically y equals 0 for a horizontal asymptote, which is the same as saying, okay, my limit is approaching 0. All right, now we got to show that it is decreasing. N plus 1 over n plus 1 squared plus 4. This is the b sub n plus 1 function. Is that less than or equal to or n over n squared plus 4. Excuse me, I should say a sub n plus 1 because we're going again. No, b. All right, b sub n plus 1 less than or equal to b sub n. Show that it's decreasing the whole time. All right, so again, not the best thing to use. A lot of foiling. We're going to get terms, just too much work. It would be quicker and easier if we take the original a, the b sub n function, turn it into an f of x function, and do the derivative test. So first derivative test, we're going to start with your x squared plus 4 squared, put it on the bottom. X squared plus 4 leads off the top. Take the derivative of the top x, which is 1. So if you want to put a times 1 out in front, that's fine. Minus then the top function x multiplied by the derivative of the bottom function, which is 2x. Okay, we clean this up. We're going to get minus 2x squared minus 2x squared. That's going to give me a minus x squared. So we have 4 minus x squared over x squared plus 4 squared. Now we want to show that this is always less than 0. So the bottom, no matter what, is always going to be positive. Remember, your x starts at 1, goes to infinity. So this is always positive. But this is the only place we can create some negatives. So just set 4 minus x squared less than 0. Let's find out and solve this for x. Add the x squared over. Take the square root of both sides. Again, we're not going to worry about negative 2 because that's outside my domain here. And if you had a negative 2, you'd have to flip the inequality symbol. So x is greater than 2. All right, so again, that's that one situation we said, even though we start at 1, from 1 to 2, you might be increasing. Then after 2, all my terms are decreasing. So this is going to be true. It's decreasing because remember we said in terms of converging or diverging, if you take the first 2 or 3 terms off and the rest of the terms converge or diverge, you put the first 2 or 3 terms back on, it's still going to converge or diverge, whatever we're looking for. So since both statements are true, this converges by the alternating series test, and now this series converges conditionally. It didn't converge absolutely, but it will converge conditionally. And that wraps up our absolute convergence.